before spring break. Next, 3 class sessions next week in spring break. And after spring break, it'll go real quick. I'll get back from spring break. So, we're getting into that final stretch, okay? That final little push. Any questions here from section 10.2? Doing sequences and series. I didn't look, see how far people have got on it. Have you done it?
I don't think we finished that chapter.
Did I not finish?
No, we just, you said just do certain ones.
That's right, I do remember that now. Oh man, I was planning to do 10.3 today.
10.2.
Yeah, I know.
What's
what I need.
10.2 do?
I got 10.2, since we're gonna finish it right now, I gotta change the due date.
Oh, okay.
And man, I planned for other stuff today, so now I gotta, we'll make this due, when is that day?
Tuesday.
24th is, yeah, well, since it's a week, I'll make it due the 26th.
Yeah.
There we go. All right, let me shut this down. So we're still in 10.2. Continued. Okay. All right, let's take a look at some limits. So I do remember now that I showed you the connection there, that the limit of a sequence, sequences are defined over the numbers that we put into sequences to calculate the list are integers, right? So sequences are not defined over the real number line. We don't put decimals and fractions in, we only put integers in. Now we could get decimals and fractions out, but we only put integers in. So the domain is a set of integers. And what we saw in that PowerPoint slide that I showed you, there's a theorem that connects the limits of a sequence with the limits that you learned in first semester calculus. Remember that? Did that on Wednesday? It's all on the slide. So that means all of the methods that well, let's say it this way. That means when we have a limit of a sequence, we can write it in terms of x defined over the real numbers, and we can use all of the methods we learned in first semester calculus. So so when we have something like a sub n equals 3n cubed over n cubed plus 1. Okay? The limit as n goes to infinity of a sub n, so the limit of this as n goes to infinity is the same or is equivalent to the limit as x goes to infinity of this expression written in terms of x. So it's that theorem we saw on Wednesday that allows us to write this in terms of x and now apply all of the methods that we learned about limits in first semester calculus, including, if necessary, L'Hopital's rule. It's not going to be necessary here. Now, for this limit, we have a polynomial on top, it's actually a monomial, and a polynomial on the bottom. And when their degrees are the same, the limit as x goes to infinity is the ratio of the leading coefficients, right? So this is equal to 3 over 1, which equals 3. And that's all there is to that. You guys good with that? All right, let's take a look at another one. This one's a little bit more complicated. Let's actually erase this. Let's suppose we have the limit, well, let's say a sub n equals n plus 5 over n in parentheses raised to the nth power. Before we do this, E is going to come up in this problem, the number E. What is the number E? Yeah, the decimal approximation for E is 2.71828, and it goes on forever and ever and ever. It's a number like pi. Have you ever seen where E comes from? Anybody seen how we derive E? No?
Kind of.
Okay, get your calculators ready. I'm going to be erasing this, you don't have to put it in your notes, but I want you to see this. Let's suppose we have the expression sorry, 1 plus 1 over n raised to the nth power. Now, before we do that, what is this? The limit as n goes to infinity of 1 over n, what's that equal? What's that? 0. As the denominator goes to infinity, this gets infinitely small, correct? And that approaches 0. How about the limit as n goes to infinity of 1 to the n power? What's that? 1. 1 times 1 times, or 1 to the 1 is 1, 1 squared is 1, 1 cubed is 1. It's always 1, right? So this is approaching 0, which means this inside the parentheses is approaching 1, because it'd be 1 plus 0. And we're raising that to the infinite power. What would be going on there? Let's make a table here. Okay? Let's put some numbers in for n. I mean, if you put in 1, this is n here. If we put in 1 for n, we're going to get 1 plus 1 over 1 is 1. So we're going to get 1 plus 1 raised to the 1 power. That's going to equal 2. If we put in 2 for n, 1 plus 2 to the second power, come on, Miss Reimer. What am I doing? 1 plus 1/2 to the second power. Work that out. What do you get? 2.25? Is that what I heard?
Yeah.
Okay. All right, well, let's get this moving. Let's put in 10 for n. Now, think about this. 1 plus 1/10 to the 10th. 1/10, let's think in decimal form. That's going to be 1.1, right? Is that correct? Decimal form? What do you get for that?
1.21.
1 point what?
21.
Is there any more?
That's it.
That's it?
Yeah.
1.21.
Got 2.59.
There we go. Yeah, check your calculation there. See what's going on. Is there any more, or is it just that 259?
It's like 2.93, 7, 4.
Okay, give me a whole bunch. 2.59374. Got any more?
2.46.
246. Figured it out?
Yeah.
All right. Now, if we put in, that's not growing very fast, is it? Let's get this moving. Let's put in 100. So 1 plus 1/100 to the 100th power, that's like 1.01 to the 100th, right? I want you to see the decimal pattern so that when we do these larger numbers, we can just throw it in there real quick. Give me a whole bunch of decimals for that. What do you get?
2.704813.
One what?
13.
3?
82.
That'll be good. All right, let's do 1,000. So that'll be 1.001 to the 1,000 power. Two point
716923932.
Okay. Let's put in 100,000. Now let's look at the pattern here. When it was 1,000, 1 was in the third decimal place. There's 2 zeros and 1. So with 100,000, there's going to be 4 zeros and a 1. 1.4 zeros to the 100,000, so 5 zeros up there in the exponent. What do we get out of that?
2.718 268
Okay. Let's go to 1,000,000. So 1,000,000 has 6 zeros. So this one will be in the 6th decimal place, separated by 5 zeros. So 1, 2, 3, 4, 5 to the 1,000,000th power, which has 6 zeros. What do we get there?
2.718280469.
280,469?
Yeah.
Let's do one more. Let's do 100 million. See if your calculator will even do that. So 100 million has 8 zeros. So this is going to be 1 point. It'll be in the 8th decimal place, separated by 7 zeros. 2, 3, 4, 5, 6, 7, 1 to 1 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. What do we get there?
2.718281815.
1,8.
15.
This first digit too, it's not gonna change, is it? No matter how large we go. That 2 is locked in. That make sense? This, once we got to here, the 7's not changing either, is it? So, the 2 locked in from the very beginning, the 7 locked in right here, the 1 is locked in beginning there, the 8 is locked in, this 2 is locked in, I know because I already know what's going on here, this is locked in. As we go further and further and further down this list, more and more digits are going to lock in. Does that make sense? Whatever number that is, when all the digits to infinitely many decimal places have locked in, whatever that number is, that's E.